so I'll just get started then. First I want to say thank you so much for being here today and taking the time to come listen to my presentation. I know there's a lot of really amazing presentations going on right now, so I appreciate you being here at mine. So for those of you who don't already know me, my name is Natalia Hussey-Burdick, and I'm an undergraduate biology major here at the University of Hawai'i. Now, the honors program has presented me with a wonderful opportunity to perform some undergraduate research, and I could do it on any topic that I wanted. So I decided I wanted to do a project on renewable energy in Hawaii, which is kind of a broad topic. Hawaii has an abundance of natural resources, so a lot of renewable energy technologies work really well here, where they don't work so well in other areas of the world. For example, solar power, everyone's favorite renewable energy technology, works well here because, quite frankly, we get a lot of sunshine. And that might seem pretty obvious to us here, we're used to it. But there are other areas in the world that don't get as much sun as we do. For example, Seattle, Portland, and London especially are notoriously dark and gloomy all the time. And this is true. I actually just studied abroad there, and I took this picture myself. It almost every day really did look just like this. So solar power wouldn't work so well there. Another renewable energy technology that's really popular in Hawaii is wind power. This is the Kauailoa wind farm on the north shore of Oahu. And it works well here because we have some pretty reliable trade winds, and it wouldn't work so well in an area that doesn't get as much wind. We also have active volcanoes here, so we're one of the only areas on Earth where geothermal energy is even an option. And the kinds of new technologies they've been developing for renewable energy are really pretty astounding. They've even found a way to harvest the fat and lipids that grow within the cells of algae and turn it into biofuel, which can be used as biodiesel to power diesel engines. So all these renewable energy technology options that I mentioned, and the ones the multitude that I didn't have time to mention, they all have substantial potential to do a lot of good for Hawaii and to reduce our dependence on imported fossil fuels, which is really the bottom line here. Hawaii imports crude oil, mostly from Southeast Asia and the Middle East, and it gets refined at one of our two local oil refineries in Kapolei that have a combined total refining capacity of 148,000 barrels a day. And I want to point out that although those refining plants are probably not always operating at maximum capacity, this statistic does not include the amount of already refined petroleum products that also come into Hawaii on a daily basis. So this 148,000 barrels of oil a day gets refined and turned into mostly marine fuel, jet fuel, and approximately 20% of it gets sent to HECO to power the generators that run our local electrical grid. Now, Hawaii is one of the most geographically isolated land masses in the world, and this practice is simply not sustainable. Eventually, it's just going to become too expensive, and we're going to have to find another way. So when deciding what kind of renewable energy technology to go with, I noticed, and I think a lot of you probably noticed too, Hawaii is surrounded by the powerful, unrelenting waters of the Pacific Ocean. Ladies and gentlemen, this is quite literally a sea of kinetic energy that can be harvested and stored with the use of just a few simple machines. And I'll talk more a little bit about the machinery in just a minute, but first I want to get into what exactly is wave energy. So the technical term for it is hydrokinetic energy, and that's not the same thing as OTEC, or ocean thermal energy conversion. That's an entirely different way to harvest energy from the ocean. So hydrokinetic energy, all it is taking the physical motion of wave power and transforming it into usable work in the form of electrical energy. So it's really simple. Kinetic energy in, electrical energy out. So I was wondering, why don't we use it in Hawaii? It's been around since the 1970s. It's not a new idea, and a lot of local politicians have tried to bring it up as an option, and the idea really hasn't caught hold yet, and I wondered why. So I did a little preliminary research, and it seems to be that the sticking point is usually cost. The power output generated by these machines are not enough to justify the cost of the materials and maintenance that goes into making them. So that brings me to the first part of my project. Either one of two things need to happen in order for it to become actually feasible for Hawaii. Either the cost of materials need to significantly decrease, so we need to find cheaper, more durable materials, or we need to come up with some sort of an innovative design feature to increase the maximum output of the machinery without affecting the cost. So I do want to talk a little bit about the different kinds of machines, because these machines are really cool. I'll start with the Pelamis because it was the first large-scale wave power energy converter, and it was set up off the coast of Scotland in 2004. It's known as the attenuator style machine, and it's made up of cylindrical devices that are anchored to the seabed with cables. And how it works is, in the inside of these, in the inside of the joints, there's a hydraulic ram which powers where the energy accumulates in an accumulator, and then it goes to the national power grid, to the UK's national power grid. And so this machine is rated at 750 kilowatts, and it has a target capacity factor of 25 to 40%. Now, what does that mean? So first of all, kilowatts are not the same as kilowatt hours. When a machine is rated at 750 kilowatts, it means that's the maximum amount of energy that can be coursing through that machine at any given time. So they want the target capacity to be so low at just 25 to 40%, because that's the amount of energy that they want to produce on a normal day with normal weather conditions. So we want a little bit of a wiggle room so that these machines can still operate in slightly more extreme weather conditions. So I did the numbers, and if a 750 kilowatt machine, those both came together. If a 750 kilowatt machine is operating at the target capacity, it's running at about 190 to 300 kilowatts at any given moment. So to put that into perspective, my 6-person household uses approximately 216 kilowatts per day. So what that means is that this machine, running at target capacity, can run 3,600 houses like mine for one day, and that's just when it's running for an hour. Or it could power my house for 3,600 days, however you want to look at it. I prefer the latter. So another kind of wave power energy converter is this one here. It's known as the LIMPET 500, and that was an attenuator style. This is a terminator style, and it's named as such because it's actually connected to the coastline. This one has a slightly smaller kilowatt capacity, just 250 kilowatts, and again, it's optimized to perform at 25 to 40%. So the way that it works is there's a stationary onshore design. It's got an opening at the bottom and an opening at the top. The waves rush in the bottom, pressurize the air inside the chamber, which spins a turbine, and the air flows out the top. And the real ingenious design of this, the key feature of this design is what's known as the Wells turbine. And it actually spins the turbine the same direction, no matter which direction the airflow is flowing. So essentially, it's generating energy on both the inhale and the exhale of the system, making it twice as effective as it would be with just a normal turbine. And this is the kind of ingenious design feature that I'm going to be looking for in my research. So maybe not this one in particular, but something like it that would significantly increase the output without really affecting the cost. The last type of wave power energy converter, I apologize for that, it's actually normal on my thing. This should totally be moved over a little bit. The last type of wave power energy converter that I want to talk about is known as the aquabuoy. It's a point absorber. And this one's kilowatt capacity ranges greatly depending on the size of the farm. So it's a network of these individual aquabuoy devices that are connected by cables, and it can be as small as 250 kilowatts like the last one, or as many, I mean, you can have as many as you want, so up to probably 200 megawatt capacity, which is huge. And the way that it works is the seawater rushes in through the bottom, and the seawater gets pressurized, and the seawater itself spins the turbine. So instead of air spinning the turbine, it's seawater, and it only goes in one direction, so not back and forth. This particular prototype has had multiple successful projects. This one seems to be a little bit more popular in the US, whereas the other ones are connected to the UK's national power grid. This one has had projects in Washington, Oregon, California, and even Hawaii. So this is the prototype that was developed for the Kaneohe Marine Corps base. It was developed in conjunction with Ocean Power Technologies Incorporated, and as well as the US Navy. Ran from 2009 to 2011. And again, they found that the mitigating factor here was cost. What they said in the report that they sent to Congress was that it's not quite effective enough to justify the cost. So, and they sort of said yet. So they said, you know, in time we might be able to develop more cheaper, more cost-effective materials. But the other thing that this study found was that there was no significant environmental impact for up to 6 buoys. And that brings me to the second part of my research, potential environmental impacts. So we all know that Hawaii has an extremely delicate island ecosystem, and wave power energy has a lot of different potential environmental impacts. There's a lot of different variables involved that could affect a lot of different things. First of all, some of the different types of machines have been known to affect wave heights. And we, of course, wouldn't want that. I wouldn't want a crowd of angry surfers coming after me saying, "What happened to my waves?" So I'll work with that. And then other different types of wave power machines have been known to affect the coastline. And this is already a big problem in Hawaii. We definitely don't want to contribute to that. Most of the machines also produce vibrational energies, which can affect marine wildlife. So anything from corals to the marine mammals and all the little invertebrates in between. So the vibrational energies could really have a potential negative effect. So what I'm going to do is look at existing environmental impact statements and analyze and compare them and see if I can make any similarities between Hawaii and those other environments that have been studied, and to see how it would really affect Hawaii as a unique coastline. So just to recap quickly my project objectives. So it's a two-part research project, and first I'm going to look at different ways to maximize the efficiency by analyzing costs of different machines existing, seeing if we can find possibly cheaper materials, cheaper, more durable materials. And also I'm going to look at ways to tweak the machinery to kind of increase the output. And then the second, once I find which kind of machine would be optimal for Hawaii, I'm going to look at the environmental impact in ways that it can affect the coastline, wave currents and heights, and of course the marine biology. So before I conclude, I just want to give a special thank you to the University of Hawai'i, in particular the honors program and undergraduate research opportunities, my wonderful professor, Dr. Scott Sinnott, who's helped me with my project, all my classmates and friends who have helped me edit and revise my project along the way, to you all for being here and listening to me today. And I want to give a special thank you to my biggest supporter, my mom, who's right here in the audience today. Ladies and gentlemen, it's her birthday today. So happy birthday, Mom. I just want to say thank you very much. And that concludes my presentation. Does anybody have any questions, comments, or suggestions? Because as I mentioned, this is just a proposal, so I'm definitely open to any suggestions you might have that can help me improve my research. In the back.
How much does one of these machines cost? Just a ballpark figure.
So that is actually something that was just brought to my attention today. That isn't a question that I should definitely have the answer to, but I don't yet. I'm just in the beginning stages of my research. And that's actually something that's hard to find. That's something that I've tried to find, but statistics on this are not easily just Google search and you found it. You have to actually analyze. Most of the cost information comes in cost per kilowatt hours, not exactly cost per machine.
Is this something that would have to be implemented statewide, or could private houses living on the beaches of Lanikai buy it and then?
So it definitely could. I was thinking that LIMPET one that's attached to the shoreline has potential for residential use, but I'm looking at what my project focuses on is trying to implement it as a large-scale renewable energy resource for Hawaii to try to connect it to the national or to the local power grid. And I'm looking for ways to try to actually make it profitable for someone. I don't see any reason why HECO can't be involved. And I just want to make it a win-win situation for everyone. We're going to have to change to renewable technologies eventually, so why not start now? Any other questions, anybody?
Besides the Kaneohe Marine Corps Basin, are there any other test projects, pilot projects, any businesses looking at doing this?
So as far as I know, in Hawaii, there's a lot of research going on, but not necessarily pilot projects. There are definitely a whole bunch of pilot projects, mostly in the UK. They really love wave power energy over there, because as you guys saw, solar power doesn't really work out so well for them. And there have been some on the US mainland, but it's been really slow to take off. Most of the projects involving wave power energy right now are in the research and development stage, not so much the prototype testing.
Even Manoa has nothing going on with wave.
So we have a lot of research going on, and I've been trying to contact professionals in the field, which has been more difficult than one might have thought. So there's some undergrad research going on. I think I know of one other undergrad who's doing a research project on this, but as far as the engineering department actually making a project for it, that I don't know. Anybody else have any questions? Sure.
Have you looked at, for EIS statements, any particular database such within government agencies that will address the environmental impact statements?
I was unaware of any databases available. If you know of any, maybe we should talk later, because I've just been doing Google Scholar searches, and mostly what I come up with is I'll get PDF files of the environmental impact statement that from the, like the website of the company who made it, and they'll say, we submitted this to Congress on this date, and here's our statement. So that's what I've been looking at so far, but of course, if you know of any databases, we'll talk later.
Yeah, definitely, because there's a lot of think tank public policy issues that do address environmental impact.
Oh, great.
If they're looking at renewable energy, this is one area it's really talk about.
That's actually one of the things that's really important to me. So as I mentioned, in the field of biology, and I was born and raised here, so environmental impact is something that's really important to me. I'm doing this to further help Hawaii, and I don't want there to be any kind of an environmental impact. So if my research does point me in the direction that says there might really be a significant impact here, then of course I would, come to that conclusion. I would say, look, we need to look at something else. Wave power is not feasible for Hawaii. Anybody else? All right, thank you very much.